Hello, this is Christy Patton Works, and this is a video for ChemEng 4096. In this lesson, we'll be starting to look at Chapter 6 of our textbook, Understanding Process Conditions. Our goals here are to start looking at what typical ranges for temperature and pressure should be, and when and how we need to justify our choices of operating conditions. As you see in the box here, the ability to make an economic analysis of a chemical process based on a process flow diagram isn't proof that the process will actually work. We need to make sure that we are operating under conditions that are reasonable. So first, let's look at pressure. A decision to operate anywhere outside the pressure range of 1 to 10 bar has to be justified. Gas pressures tend to be more economical when you have larger pressures because you end up with a smaller volume. But too high is going to cause a requirement for thicker walled equipment, sometimes specialized construction techniques for lower pressures if you're going to be pulling a vacuum. And so therefore we want to try to keep it in that 1 to 10 bar range. Temperatures should be below 400 degrees C. Now there also are some minimum temperature requirements. Most processes, minimum temperatures are not a concern, but our materials are going to lose physical strength at higher temperatures and they'll become brittle at lower temperatures. So we need to, always be sure that we are keeping an eye on the temperature. Anything above 400 C, 750 degrees Fahrenheit, you need to justify why you are doing that. In the book, they look at the tensile strength of carbon steel. And at ambient conditions, the strength is really good for carbon steel. But if you take the temperature up to 400 degrees, you've lost 18% of that strength. And if you take it just another 150 degrees, you've now lost 2/3 of the strength, going from 400 to 550. So we try to avoid operating at those other conditions, and if so, we're going to need to change materials to find something suitable. Now, stainless steel isn't quite so bad at the ambient to 400 degree range, but it still is going to lose 2/3 of its strength from going from 400 to 550. So again, the magic temperature, 400 degrees C. Try and keep it below that. Although we do not have numbers here about lower temperatures, we have problems when we go into cryogenic conditions that the materials are going to become brittle and also have damaging results from lack of strength. So we're going to want to make sure that we are choosing temperatures wisely. Now most of the time, if we're trying to go for higher or lower temperatures, it's because we are heating and cooling our systems. Now those utilities have limits also. Usually the steam that we're going to have available is going to be at a maximum pressure of 40 to 50 bar. That will provide steam at a temperature of about 250 to 265 degrees C. If you need to go to these higher temperatures, say up to 400 degrees C, you're going to have additional costs. You're going to be burning fuels or something so that you can reach those higher temperatures. For cooling, we really prefer to use just cooling water. We can expect to have that available at 30 degrees C. And we'll return it to the cooling tower at around 40 degrees C, and we're going to want to try and keep our cooling needs so that those temperatures will work. Sometimes we do need to go to lower temperatures, and that will require refrigeration. That costs extra money. We want to make sure it's justified to do that. So anytime you're trying to heat to more than 260 or cool to less than 40, you want to make sure that you have a good reason for doing that because it will cost extra money. Now there are a couple of other things. On reactors, we're going to be concerned about whether or not we're getting a favorable equilibrium conversion. We also want to go for the temperature that's going to kind of optimize our reaction rate. We may need a higher temperature so that we can keep a gas phase present, or maybe choosing a higher or lower temperature will improve our selectivity for our desired product. In separators, frequently we have to operate at unusual temperatures or pressures because our concern is whether or not we have the correct phases. So maybe we need a higher temperature so that we get a vapor phase for our vapor-liquid equilibrium. We usually are going to want to feed our materials to the reactor in stoichiometric proportion. This minimizes waste. But sometimes we'll choose not to do that. Reasons might be that there's going to be an inert material in the feed. So a diluent might control the rate of reaction, which will then help control the temperature in an exothermic reaction. Or to keep the reaction from being in the explosive region. Or maybe it's just simply we're adding an inert to keep unwanted side reactions from happening. We also may need to add an excess reactant because that's going to force the equilibrium in the direction that we want. The product may be present in the feed. Frequently this is because of autocatalyzed reactions. If we need to have some of the product there for the reaction to happen, we want to make sure that we actually put some product into the feed stream. Okay? This also might happen, though, if we've added recycle streams where we had a difficulty separating the material out. Some of the other things that occasionally we'll choose to do but are generally bad ideas. For compressors, a compressor we can expect to as much as triple the pressure. If we need more than that, we're going to use multiple stages of compressors with intercoolers in between. Also, if the high temperature, or if the temperature coming into the compressor is high, we will want to cool the gas before we do the compression so that we can optimize the life of our compressor. On heat exchangers, we're typically going to look at our delta T log mean for our exchangers. Whenever we have something that has more than 100 degrees of delta T, we want to look into the possibility of doing heat integration to optimize our system. Process heaters, we want to make sure that the exit temperature is lower than the steam temperature that we're using. And we'll use high pressure steam to heat the process stream in those cases. Valves, we're going to be careful about the pressure drop that we have across that valve. If you have a very large pressure drop and you have a gas, you might want to consider putting in a gas turbine to recover some of that lost work. And finally, mixers. If the two streams that you're mixing together have very different temperatures, again, look at the possibility of heat integration as a way of minimizing utility use throughout the rest of the plant. If they have very different compositions and you're then sending them later to a separator, you might want to look very carefully at maybe separating the streams separately as a more economical approach. Finally, we have here a process conditions matrix. This is a way of kind of organizing your thoughts and making sure that you've thought through each of these special concerns for a process. So what we're going to do is we're going to organize a list of all of the equipment we expect to have in our process based on our process flow diagram, and then look at the process conditions that we are designing for at that moment. Look at the temperatures, look at the pressures, look at the feed ratios to reactors, and then look specifically at your compressors, what the compressor pressure ratio is, those exchangers, what the delta T's are, what are your temperatures on your heaters, your pressure drops on your valves, and then look at the temperatures and compositions on mixing streams. Organize these, place an X in each of these if these conditions apply, and we're going to, in class, look at how we can use this matrix to improve our designs. Thank you.